Welcome back to Physics 101. This is Lab 4, the spring mass system. Today we will be predicting the motion of an object of mass attached to a spring using Newton's second law and the energy principle. First, we get data from Tracker by following the motion of the spring in the video and the mass that's attached to it. We then uploaded that into an Excel spreadsheet, and then later in the lab we would predict the motion using our Python code. Few things we needed first in order to run the code. We needed to know the mass of the object, which was given to us in the video. Then we have the position, which we got from the data that we used in Tracker. Next, the initial velocity, which also we used the data from Tracker, the first two time points. Then we also have gravity, the spring constant, the relaxed length of the spring. Then we have the magnitude of the spring, or not the magnitude, but the L vector. Then we have L hat, and finally the stretch of the spring. Next, we come down to the heart of the code that we really need to edit. So how did we edit that? First, we need to define Fnet. And we know that Fnet is just equal to the sum of all the forces acting on the object. And in this case, that was the spring force and the gravity force. And here you can see we have the identities for those. The spring constant K, stretch S, L hat, and the mass times gravity. Then we need to find the velocity, and we can do that using Newton's second law. I've spelled it out here in units, just in case this would help anybody, because I know that it helped me thinking through the problems. Through here, you can see that the units will cancel each other out, and we will be left with meters per second. Then later, we will also need to find the position of the spring as it's moving. And we need to, in order to do that, we take the velocity and multiply that by delta t in seconds, and we get the meters. So then here in our Python code, we plugged in all of that. We have the ball's mass times gravity. Here we have the spring force. Then we added them together in order to get the gravitational, or to get the Fnet. Then finally, we plug that into our to get our velocity, and then we use the velocity to predict the ball's motion. Next, we use the energy principle in order to calculate the change in the energy, the kinetic energy, gravitational potential energy, and the spring potential energy. And here we have the formulas that we've been using all along. And again, I spelled this out into units that we are using. Ultimately, we're going to be measuring the change in energy in newtons. So here again, we first put in these equations for the kinetic energy of the ball, the potential gravitational energy, and the spring's potential energy. Then later down here in the code, we update those values in order to see the change in the potential energies and the kinetic energies, and how those ultimately affect the energy of the system. So then, we'll just go ahead and run the code here. And as you can see, the spring is oscillating very similarly to what we saw in the video. The next thing that we will do is that we will import the data that we used in Tracker into an Excel file, and then use that Excel file in Python in order to see how well our model predicts the motion. The red ball is what we measured in Tracker, and as you can see, actually our model predicts the motion fairly well. So you can see here the yellow line is the total energy of the system. Is the energy principle satisfied? Yes, it is. The energy system is constant and conserved. As you can see here in the graph, the yellow line is horizontal all the way during the entire test. So the kinetic energy and the potential energies of the spring and the kinetic and potential energies of mass, which equal the total energy of the system, ultimately cancel each other out. Then for the oscillation periods, I found that they were 1.77 in the x direction and 1.67 in the y direction. And from that, we can safely conclude that the forces that were acting in the x direction and the forces acting in the y direction were equal.